In this video, I'm going to discuss about the difference between the number of points, number of segments, and step size for the numerical integration methods or equations. But before we start this discussion, I would like to explain two main concepts that will be used in the discussion later on. First will be the name that I will use to refer to the various terms in the numerical integration equation. Okay, so based on this general form of a numerical integration, so fx will be the function to be integrated. In some other resources, you might see that they use the name integrand. Okay, and dx means this function to be integrated is with respect to x, which is the independent variable. So sometimes if you are asked to plot the function to be integrated, then x will be the independent variable, x will be the dependent variable. As for integration, you will need to have the limits of integration. So therefore, we do have upper limit and lower limit given at this location in the general form. And the final answer or the final result will be the integral. So this is the area under the curve, and the curve here means fx. Or in other words, we can say that this is the area under the function to be integrated. So that's what it means by this phrase here, an area under the curve, comma fx. Okay, so fx doesn't refers to the result I. I'm just trying to indicate that we are looking at the area under the function to be integrated, which the function to be integrated, we use the notation fx. These are the names or terminology that I will use in the explanation later on. The second concept that I would like to highlight is the relationship between curve fitting and numerical integration. So let's take trapezoidal rule for example. The dark blue line, as you can see here, is the function to be integrated. Therefore, it is fx. And the black solid line is the line that trapezoidal rule used to approximate the function to be integrated. So in other words, this means that trapezoidal rule assumes that the black solid line can be used to represent the function to be integrated. Okay, and we can see that from this diagram, the error will be relatively big. For trapezoidal rule, we need 2 points to find this approximate line that we use to approximate the function to be integrated. Because of trapezoidal rule assumes that the function to be integrated is a straight line. So therefore, the straight line equation has 2 coefficients, which is ax plus b, so it's a and b. Therefore, we need 2 points. Okay. Now let's look at Simpson's rules. We have Simpson's 1/3 rule on the left and Simpson's 3/8 rule on the right. So let's look at Simpson's 1/3 rule. Simpson's 1/3 rule uses second order polynomial. So which means the dotted line represents the function that we use to approximate the function to be integrated. So we are assuming that this quadratic line is the same as the function to be integrated. So we can see that the error is much lesser than the trapezoidal rule. Okay, quadratic line means it uses a quadratic equation which is in the form of ax squared plus bx plus c. So we have a, b, c, 3 coefficients. Therefore, we need 3 points to apply Simpson's 1/3 rule 1 time. So then only we are able to solve for the coefficient a, b, and c. And with the same concept, Simpson's 3/8 rule will be using 4 points because it uses a cubic line or cubic equation. Cubic equation will have the general form of ax cubed plus bx squared plus cx plus d. So we have a, b, c, d 4 coefficients. Therefore, we need 4 points to identify this equation, which is the best fit line that we use to assume that it is the same as the function to be integrated. As we can see in the right hand side diagram, the dotted line, which is the cubic function, gives even closer estimate to the function to be integrated. Okay, so this is why Simpson's 3/8 rule requires 4 points to apply 1 time. Okay, so with these two main concepts, we will start our discussion related to the number of points, number of segments, as well as the step size. We will start with trapezoidal rule. As we have explained just now, trapezoidal rule uses a straight line to approximate the function to be integrated. Therefore, to apply trapezoidal rule 1 time, I will need 2 points, x1 and x2, so that I can get the straight line equation. Okay, so this is what happens when we apply the formula given for trapezoidal rule. Okay, if I have 2 points, that means I have one segment. Okay, and the step size will be the width of a single segment. So in this case, I have only one segment. So the step size will be the width of the entire segment. So this is trapezoidal rule. Let's look at composite trapezoidal rule to identify how the pattern of these parameters changes. So in this example here, we apply composite trapezoidal rule with 6 points. So we have x1, x2, x3, x4, x5, and x6. If we have 6 points, that means we will have 1 segment, 2 segments, 3 segments, 4 segments, and 5 segments. Okay, so there is a small distortion in this diagram. We need to assume that all 5 segments are of equal width. Okay, then only we can apply composite trapezoidal rule. So we can see here that if I have 6 points, I will have 5 segments. So the number of segments is always 1 less than the number of points. And the step size is still the width of a single segment. So in this case, within the same range of A to B, because I have 5 segments now, so the width is smaller. So this is the width of a single segment, which is the step size. Okay, so that's how we could actually identify the number of points, number of segments, and the step size. So if we identify these 3 parameters in the way that I have explained just now, it would be much easier, and it is very unlikely that you will get it wrong. So let's try to apply the same approach to identify the number of points, number of segments, and step size for the Simpson's one-third rule. For Simpson's one-third rule, single application of Simpson's one-third rule requires 3 points because we are looking at quadratic equation as the approximation for the function to be integrated. So therefore, I have 3 points, x1, x2, and x3. So this also means that when I apply Simpson's one-third rule one time, I will need 2 segments. And the step size will still be the width of the single segment. So because there are 2 segments here, so the step size is this width. Okay, so it's not the entire range of the integration limit from A to B. Okay, let's extend this concept to the composite Simpson's one-third rule. In this example, at the right-hand side diagram, we have x1, x2, x3, x4, x5, x6, x7, x8, x9, x10, and x11 from A to B, and they are all equally spaced. So I am applying composite Simpson's one-third rule with 11 points in this case. So composite Simpson's one-third rule means that we are applying Simpson's one-third rule multiple times. Every time I apply Simpson's one-third rule, I will use 2 segments. So for the second time that I apply Simpson's one-third rule, I will use 4 segments. The third time I apply Simpson's one-third rule, I will use 6 segments. The fourth time will be 8 segments, and the fifth time will be 10 segments. So we can see that the number of segments is still 1 less than the number of points. It will be always the case. Okay, and the step size is the width of a single segment. So in this case, the step size will be much smaller because we have 10 segments in total within the same range of A to B. There is another quick concept that I would like to highlight. Take note that when I apply Simpson's one-third rule for the first time, I need 3 points, which is x1, x2, and x3. And when I apply Simpson's one-third rule for the second time, I need 3 points also, and these points would be x3, x4, and x5. Okay, and the third time, it would be segment 5 and segment 6, so that will be x5, x6, and x7. So what I would like to highlight is that applying Simpson's one-third rule one time requires 3 points. Applying Simpson's one-third rule 2 times doesn't double the number of points because, as we can see here, x3 is used in both applications, the first application and the second application of Simpson's one-third rule. So same thing, we can also see that between the second application and the third application of Simpson's one-third rule, they both use the point x5. So this is something to take note. Okay, so if you try to sketch the number of segments and then based on the number of segments, identify the number of points, it would be much easier and very unlikely to make mistake. So this is the explanation that I would like to discuss about number of points, number of segments, and step size. You can apply the same concept to Simpson's 3-8 rule as well, and also composite Simpson's 3-8 rule.